So today I'll be teaching you about limits. Limits are a fundamental concept used often in the studies of graphs. To give you an idea of when this is introduced to students in the public school system, most students learn limits at the end of pre-calculus. However, as is consistently my opinion on the education system, we as GT students, despite the fact that we may be freshmen, we still have the ability to learn this interesting material. To be more specific, limits are used in the formal definition of the derivative, as we've already seen before. As you can see right here, it has this limit here. Limit as h approaches 0 of this function. So we've already seen that before. Hopefully, by the end of this video, you'll have a better understanding of what this limit really is. So that can be considered the first example of limits. Now, the second example is something you may have already seen before in Algebra 2, which is something called end behavior. Now, this is kind of a big one for me. It has bothered me slightly that in Algebra 2, we have been taught what is called end behavior. The concept itself is fine. It is acceptable, even perhaps a requirement, that students identify what value a function approaches as x approaches infinity or negative infinity. However, I think that there should be a better notation for this process. Instead of calling it this end behavior, the instructors should at least give it another name to sort of clarify to the students. And I would call that the limit as x approaches negative infinity of the function, and the limit as x approaches positive infinity of the function. And that's what the students should be required to find. Now, moving on, thinking of other uses of limits, other than the formal definition and end behavior. There are actually many different theorems involving limits, including something called L'Hopital rule, and also another thing called the squeeze theorem. And these things, I believe, can be proven, and they, involve limits, and are very interesting things which we will study later. Now, the fourth example that I would like to show you is the small angle approximation for the sine of x. Small angle approximation. Sine of x. And we'll look more at that later. Continuing our lesson on limits, let's assume we have a piecewise function f of x, where f of x equals 2 for any domain value of x that is not equal to negative 2, and at negative 2, f of x is actually at negative 5. So if we see the graph of this function, which is right down here, the graph, what do we know about this graph? Well, we know that the function the function at -2 is equal to -5. Sorry, I want to make sure you can see that. So f at -2 equals -5. Now, to give you another example of a limit and how it's used, we can say the limit as x approaches -2, as x approaches this value of -2 of f of x. We can find this value a variety of different ways. Now, first of all, we can take a look at the graph, and because it's a piecewise function, and we have the graph right here, it helps us very much when we're finding this limit. Because we know that as I've said before, for all values of x, f of x is consistently equal to 2. Except for when x is equal to -2. At the value x equals -2, f of x is -5, which is quite different from the rest of the function, as is clear from the graph. But what this limit is asking is the value the function approaches, not what it's defined as, but what value it approaches. So in this case, we can just say, from looking at it, that through these values coming closer and closer to -2, closer and closer to x is equal to -2, this f of x approaches the y value that is +2. And the same can be said for the left side. As x approaches -2 from the left, it approaches the exact same value of +2. So we know, therefore, that the limit as x approaches -2 of the function is equal to 2. So that should give you a basic idea of how to find these limits. We can look at the graph, that is one way. First, I would like to explain the difference between these three expressions here. First of all, allow me to say that the limit as x approaches a of f of x sometimes does, but does not have to equal f at a. So I'm going to write that. So the limit as x approaches a of f of x does not have to equal f at a, because sometimes the function is not defined at a, which we will see later. And the difference between these two expressions right here, the limit as x approaches a plus, we have a plus there. And what that means is we're taking the limit as x approaches a from the right. Or rather, to be more technical, the x values approach a from the positive values. So let's say we wanted to find, it's fair to do this in calculus. If we had, for example, f of x equals the log of x, sorry, this is where I am. F of x equals log of x, the common logarithm of x. And as we've learned in algebra, the logarithm is basically the inverse of an exponent. So we have this graph right here, and we know that you may have seen this before, that logarithmic functions approach negative infinity. This negative infinity on the y-axis, or f of x. Y equals f of x, of course, and then this is just the x-axis. But on the y-axis, these values of log of x approach negative infinity as x gets closer and closer to 0. But you may remember, for logarithmic functions, well, logarithmic functions are not defined in the second and third quadrants in the real number system. But we do know we can use limits here too, and we can say that the limit as x approaches 0 from the right of f of x equals negative infinity. And an interesting property of limits is that they can be equal to positive infinity or negative infinity. But in this case, if we have log of x, the reason we can't say the limit as x approaches 0 is because really this function is not defined where x is negative. Which means that, well, what I'm trying to say is, on a more broad scale, if we're taking the limit as x approaches a, with no specifications from the left or from the right, it basically is assumed that it includes both of these. That both of these limits exist and are equal.